Hi, welcome to ECE/CSC 506, and today we are going to talk about module 1.2 or power wall. In the previous module I have talked about the switch from single core design to multi-core design that occurred between 2001 and 2005, and I mentioned that the switch was motivated by several factors, but they were related in the sense that there's a disappearance of low-hanging fruits in exploiting the instruction level parallelism. Instruction level parallelism relied on increasing the pipeline depth, and increasing the pipeline depth bump into the increasing overheads of the pipeline latches, resulting in less and less things that can be performed in a single pipeline stage. And in addition, increasing the pipeline depth does not necessarily make the critical loops any faster, right? So if the pipeline depth doubles, the size of the critical loops also double. So there is a diminishing return from increasing pipeline depth. Increasing pipeline width is another method for exploiting instruction level parallelism, but again they had suffered the same problem in that increasing the pipeline width incurs a quadratic increase in the complexity, at least. And the third problem I mentioned is that power efficiency has declined significantly for instruction level parallelism. All these factors prompt designers to switch from single core design to multi-core design. Now let's look at the last problem, which is power efficiency. In this module, I'm going to talk specifically on that topic because it's projected to be something that will be very important in the next few decades. So before continuing, let's look at the basics of power and energy. So energy essentially is the ability of a physical system to do work on other physical systems. The standard unit for energy is joule. To give you some idea, 1 joule is the amount of energy needed to lift an apple from your hand to a shoulder height. Or 4 joules is roughly an energy needed to heat a teaspoon of water by 1 degree Celsius. Now what is power? Power is the rate at which energy is transferred or transformed from one form to another form. The unit is watt, and 1 watt is essentially 1 joule delivered in 1 second. In the context of electronic devices, power can be obtained by multiplying voltage with current. For a capacitor, the energy that can be stored is 0.5 times capacitance C times voltage square. If the capacitor is drained and charged at the frequency of F per second, then the power that is consumed is the following. So the power is total energy that is drained and charged in 1 second. And because there is draining and charging, that will be 2 events. This will be multiplied with half times CV square times the frequency of that switching, which is F. So we end up having with CV square F. The above is referred to as the dynamic power consumption. Alright, now let's look at energy efficiency. Energy efficiency essentially defines how much energy is required to perform a work. The unit will be energy unit, right, or amount of energy divided by the work unit, or the amount of work. One example of energy efficiency figure is EPI, or energy per instruction. How much energy on average to execute one instruction. So the higher the EPI, the lower the energy efficiency. Another way of looking at energy efficiency is the ratio of how fast energy is consumed versus how fast work gets done. The unit here is the power unit divided by throughput unit. So, for example, it may be watt per instruction per cycle, which is a throughput unit, watt divided by instruction per second, or it can be watt per floating point operation per second. If we choose the middle one, which is watt per IPS, then the watt is itself is joule per second, IPS is instruction per second, and then the seconds eliminate one another, and then what we have is the joule per instruction, or essentially the same with EPI. Alright, so watt per throughput is also a possibility, right? So joule per second divided by work per second. This essentially leads to joule per work, or amount of energy required to perform work. So notice that regardless how they are computed, they result in a similar metric, EPI. There are also other metrics that if you go to literature, read computer architecture papers, you can see other metrics. For example, energy delay product. Now, what is energy delay product? Essentially, when we talk about the energy required to perform work, it matters most in a mobile system where you have limited amount of batteries, amount of energy stored in the battery. However, people have preferences towards getting the job or the computation done earlier. So for example, suppose there are two systems, system A and system B. System A gets a work done at 0.5 watt in 2 seconds, or system B gets a work done at 1 watt but in only 1 second. Okay, so system B is faster, but it consumes more power. So if you look at the energy usage, they are equivalent. Okay. However, we have preference to choose or to buy system B because it can get the same job done quicker. But therefore, in order to give a preference towards faster systems, then people have come up with energy delay products. So the energy is then multiplied with the delay. There is also another metric, or energy delay square product. And what is this? Well, essentially it comes from the same rationale as the energy delay product, but it increases the weight given for delay, right? So it emphasizes on reduction of delay more than in the reduction of energy, right? So knowing all those basic metrics, now let's look at the power wall problem in microprocessors. So a microprocessor consumes two kinds of power, dynamic and static. The amount of power that the microprocessor can consume is determined by the packaging constraint. So for example, for a desktop or laptop systems, typically people quote 65 watts. Now note that 65 watts is similar to a light bulb, so it's running really hot. It generates heat, and the heat has to be dissipated. If the packaging is unable to dissipate the heat will accumulate, and this will make the electronic device failure. it will melt. It will essentially melt. So essentially, it's critical for the heat to be removed at the same pace as it is generated. Okay? So for desktop and laptop, that limit is roughly 65 watts. Now, if you use liquid cooling, then the limit may be higher, okay? Maybe significantly higher, but at the expense of bulkier system and also more expensive. Now, there are two sources of power consumption. One is dynamic, the other is static. Dynamic power is power consumed from charging and discharging of capacitive loads. Okay, and therefore the formula is very similar to the formula when a capacitor consumes energy, right? So essentially, dynamic power is equivalent to ACV squared times F. A is the fraction of gates that are actively switching, C is the capacitance, V is the supply voltage, F is the frequency of switching. Now, if there is no transistors that are switching, it turns out that a microprocessor will still consumes power, and that comes from a leakage. Okay? Essentially, there is insulator that is not perfect, so it's leaking some current, and that current that leaks essentially produces power consumption called the static power. And static power consumption formula is simple. It's essentially the voltage, supply voltage, times the leakage current. Now let's look at a formula in which how is the supply voltage and the frequency related. Alright, so here the formula is essentially the maximum frequency the circuit can operate is roughly equivalent to some constant multiplied by the voltage drive. Okay, voltage drive is the difference between supply voltage and the threshold voltage, in parentheses, raised to the power of roughly 1.3, and then divided by the supply voltage. Now, what is the threshold voltage? Threshold voltage essentially voltage level that is required to make transistor conductive. Right? So, if we plot this figure, here we can see the x-axis as the threshold voltage, the y-axis is the maximum frequency. You will see something like this. Now, don't pay attention to the scales. These are just fictitious scales. So what we are interested in is in the shape of the curve. Okay? So when you reduce the threshold voltage, so we go to the left on the x-axis, we see an increase in the maximum clock frequency. Okay? So essentially, in order to improve clock frequency, you can do that by increasing the distance between the supply voltage and the threshold voltage. Alright, now how about the static power consumption? What does it determine? Okay, so let's look at the leakage current. The leakage current is essentially larger than the exponent raised to the power of minus Q threshold voltage divided by KT. T is temperature. The important thing here is the following. So that threshold voltage also shows up in this formula at the exponent. If we plot this curve, we will see something like this. The x-axis is the threshold voltage and the y-axis is the leakage current. As we reduce the threshold voltage, leakage current increases exponentially. Right? Now, with the nature of exponential function, essentially, if there's a significant acceleration of the quantity beyond certain threshold, right? So it turns out that in the past few decades, we can think of it as the exponential function has been there for a long time, but the absolute magnitude of the leakage current was small, thus we can ignore it in the last few decades. But the projection is that in the next few decades, or let's say next 20 years, we're going to see a huge acceleration of leakage current if we decide to reduce the threshold voltage. Okay, so thus reducing threshold voltage increases static power consumption exponentially. So we are presented essentially with a dilemma. Do we decrease threshold voltage, or do we keep it constant, or what? Or do we increase it? So if we decrease the threshold voltage, we improve performance because we can clock the circuit faster, right? Hence, we can improve performance. But decreasing the threshold voltage also increases leakage current exponentially. Hence, either it improves performance or it increases, improves performance and at the same time increases static power consumption. Or the other choice is to keep threshold voltage constant or increase it. Now, the consequence of this is very, very significant. Okay. In the past, we can, or let's say before multicore, we can pretty much ignore the static power consumption. It's not very important. Okay, here is the back of envelope calculation. Okay, so let's say the gate length or transistor size scales every generation by a ratio of 0.7. Okay? 0.7 means 30% reduction in the next process generation. Let's say capacitance scales by 70%, obviously because the gate length declines. And the gate length declines also enables transistor to shrink by 30% in one dimension, or 50% if we measure it as an area. So that therefore we can fit twice as many transistors on a die, right? So number of transistors scales by 2 times. And the supply voltage, let's say, because the threshold voltage can be reduced, the supply voltage can also scale down by a factor of 0.7. And the frequency, let's say it can scale by 1 divided by the ratio, which is 1.4. And if we look at the dynamic power consumption in a new process generation, we'll see the following. Okay, so the original dynamic power consumption is ACV square F. Now it is A prime times C prime times V prime square times F prime. Now A has increased. A prime is double or 2 times A because we have twice as many transistors. C prime is 0.7 of C. V prime is 0.7 of V. And F prime is 1.4 of F. If we multiply them out, we will see that these constants cancel out each other, resulting is in ACV square F, which is exactly the same as in the previous generation. Okay, so essentially we see that the power consumption of the chip or of the die has not increased. However, when the threshold voltage cannot be reduced, we have a big problem. Okay, let's take a look. So let's say capacitance will scale by 0.7, number of transistors scales up by twice as much, but supply voltage cannot scale because the threshold voltage cannot be scaled down, right? So we plug in everything as the same, and let's see what happens. So the original dynamic power is ACV square F. The new dynamic power is A prime, C prime, V prime square, and F prime. There are twice as many transistors, 2A. There's 0.7 of the original capacitance. Now the voltage is the same as before because of the threshold voltage cannot be reduced. And then there's 1.4 F. So what we have is essentially dynamic power consumption in a new process is 2 times the dynamic power consumption of the previous process generation. Okay, so essentially this means we double the power consumption of the die. And if you think about it, if we start off with 65 watts, if we double it, that's going to be 130 watts. If we double it again, 260 watts, and so on. So it becomes extremely hot and we can't really cool it down. Okay? So that spells trouble. The implications for architecture design are the following. So clock frequency cannot be increased. Hold on. Yeah, clock frequency cannot be increased much. Okay, essentially because we have to somehow offset the doubling in an increase of power consumption. One way to do it is to halt the clock frequency increase. Second is that we still can put lots of transistors, double number of transistors every let's say 18 months to 3 years. We still can do that, but the power consumption is scarce. So that means we're gonna have declining power budget per core. And any new architecture in the future will have to improve energy efficiency just so that it can improve performance. Okay? And the dominant metric will be performance per watt or number of operations per joule. Alright, let's look at the first effect. Increasing clock frequency has hit a dead end. Now, is there any evidence to that? Let's look at the following. So the following curve essentially shows processors from 1971 until 2012. And these are essentially a bunch of commercial processors, and we plot that their clock frequency on this chart. The y-axis is logarithmic scale. Okay? So we can see that between 2001 and 2005, something has changed. Okay? Prior to that, we have increasing clock frequency, right? In fact, the increase is actually slightly faster than exponential. Okay. If it's exponential, it will be straight line, but here this curve is increases faster than a straight line. So there has been super exponential increase in clock frequency, except that at 2001 to 2005 suddenly it just stalled. Okay, now remember what happened during 2001 2005. There's something else happened, and the thing that happens is essentially the transition to multicore, right? So here essentially we can see that the increase or the switch to multicore is related to the stagnation in the clock frequency, which suggests that is related to the power wall problem. Now let's look at the impact of the stagnant clock frequency. What happens to the pipeline depth? Okay, here this figure shows the same time frame, but the y-axis is the number of gate delays per pipeline stage. Okay, now we can see that as we approach 2001-2005 time frame, we have a big decrease in a gate delay per pipeline stage. Essentially, we slice the pipeline stage into more and more stages. Except that after 2001-2005, the trend reverses, which means we cram more gate delays on a single pipeline stage. We tend to do more in a pipeline stage than before. Now, is this all enough to cap the power consumption on a die? Alright, the next curve essentially shows the clock frequency, keeping the clock frequency between 2001-2005 turns out not to be enough in capping the power consumption. Okay, so there are two set of data points here. The projected power is obtained by technology parameter, voltage, frequency, and so on. It shows increasing trend, but the actual power kind of like stagnates between 2001-2005, which means essentially keeping the clock frequency constant itself is insufficient, because it would have followed the blue points here. So there must be something else that kept the power consumption stagnant, which is essentially what the heroic measures such as power clock gating and so on that people employ. Right? So exercises. Here are the two problems. Please work on this, and questions come in the next few slides. So let me conclude this module essentially by saying that the switch from single core to multi-core is essentially caused by and is extremely related to the power wall problem. Essentially, the fact that we cannot reduce threshold voltage as we enter new process generation. Okay, and this problem is as intricately linked with the increasing the pipeline depth and pipeline width, because increasing pipeline depth doesn't improve performance much, but it increases power consumption by a lot. Increasing pipeline width quadratically increases complexity of the die at the same, which means quadratically increasing the power consumption. So therefore, because we have a power wall, then those things have to be abandoned. Alright, so in the next module, I'm going to talk about perspectives of parallel computers. Until then,